Hello and welcome to this Coats cast, driving down environmental impact. Composites make the automotive world more sustainable in partnership with INEOS. Before we get started and I hand you over to our presenters for today, I just want to go over a few items so you know how to participate in the event. We will be sending you a recording via email after the webinar has finished, so please don't worry if you miss something. You can always go back and revisit the session afterwards. If you do have any questions for our presenters, and we very much hope that you do today, please feel free to submit them by using the questions pane in your GoToWebinar control panel. Usually this is on the right-hand side of your screen, but it might look a little bit different if you're using a mobile device. We're going to continue or collate all of these questions and go through as many as possible at the end of our presentation today in the allotted Q&A time. Finally, we do have a couple of handouts for you to download today from both Coats and INEOS. So please do make sure you have a look at those. They are also in your GoToWebinar control panel for you to download. Now, just quickly running us through the agenda for today. First of all, it is going to be the Coats team taking you through reinforcement technologies. Then we'll be hearing from INEOS on the resin technologies that they have to offer. And then we'll have a quick summary at the end, along with questions. So without further ado, I'm going to introduce you to today's speakers. John Ilka from Coats, George Hahn from Coats, Dan Dodal from INEOS Composites, and Jonathan McKay from INEOS Composites. Over to you, John.
Sarah, thank you. I'm excited at the opportunity to present Coats Lattice technology today. A quick background on Coats. Coats is the largest global supplier of industrial threads and yarns. Our 2020 sales were approximately 1.2 billion, and we have 18,000 global associates. Coats is a publicly traded company on the London Stock Exchange, and our beginnings date back to the 1750s in Scotland. Coats belongs in both the FTSE 500 and the FTSE for Good. My focus today will be on the lattice and lattice conductive product lines, which, as you will see, are an innovation based off of our 250 years of sewing expertise. Next slide. Coats is comprised of two business units, apparel and footwear and performance materials. We belong in the performance materials division and are focused on composite preform technology. Next. Coats has a 250-year history of investing in innovation. We have 3 global innovation centers, one in Sevier, North Carolina that focuses on automotive composites, one in Bursa, Turkey that focuses on energy and sporting goods, and one in Shenzhen, China, focusing on apparel and footwear. Each of Coats' facility is built for a collaborative innovation process with our customers. Each center includes an innovation gallery detailing our technology by markets, a material labs for development and evaluation of new material technologies, and a pilot/prototype plant to produce production intent materials for evaluation. Next slide. In discussing preforms, let us evaluate the current value chain. So if we evaluate the current value chain for the production of molded composite articles from continuous fiber reinforcements, we see that either a fiberglass roving or carbon fiber tow, or both, are used to produce a NCF or other broad good technical fabric with a preset layer orientation. The ply patterns are cut from the broad good fabric and stacked either manually or automatically in the necessary ply or layer orientations. As you can see from this process, it results in significant waste in cutting the patterns from the broad good and allows errors in the stacking of the ply patterns and schedules. Waste can be as much as 20 to 50%. Next. The lattice process is unique in that it allows us to fabricate near net shape continuous fiber preforms directly from either fiberglass roving or carbon fiber or both with no waste. we receive a 3D CAD model from the customer and use software to convert the 3D form into a flat two-dimensional pattern. We then program the customer's fiber orientations to develop the 2D lattice preform. The preform is converted into machine language, and we use our multi-head TFP machines to fabricate the near net shape preform. Versus conventional technology, the lattice preform costs less due to no waste and elimination of labor, and results in a higher quality and more reproducible preform. Next slide. This slide details the product development cycle and Coats business model for the lattice preforms and Coats part in the value chain. The orange box details Coats activity in the value chain. Coats, again, receives the CAD data from either an OEM or Tier 1, converts it from 3D to 2D lattice preform. Based on the part design, the fiber paths are digitally laid out. The design file is converted to G-code, and we print the preforms to net shape, buying reinforcing fibers from various material suppliers. Coats' business model is to sell near net shape preforms. In this case, we would sell a preform to a molder and mold the parts, and the molder would mold the parts using either RTM or liquid composite molding. Next. Coats is very focused on sustainable development on a global basis, with 50% of our raw materials coming from renewable/recycled feedstocks by 2025. For composites, we are evaluating natural fiber reinforcements and backing materials made from recycled streams. On the thread side, we are using biodegradable and recycled stitching threads. We are on a path to achieve 25 to 45% recycled content, and simultaneously will evaluate the overall effect using life cycle analysis to validate all steps forward. At this point, I'd like to turn it over to George.
Thanks, John. In these next few slides, I will go over the opportunities TFP offers. At its core, TFP, or tailored fiber placement, is an additive process where we secure material where material is required. This allows us to design complex parts in a new light, and the following examples showcase how TFP handles projects typically with high off-fall waste. The paths that you see here all represent fiber paths of material to be added in building up the composite laminate structure. Next slide. So again, as an additive process, TFP builds in layers, which allows us to design laminate structures with varying thicknesses. We call our TFP product a preform, and in a preform, we can vary the thickness to represent different part features. In the left example, you can see how the preform of an aero structure is designed kind of like a topographical map. In the top right represents a beam member with a thicker middle region that tapers towards the fastener locations on the ends. And finally, in the bottom right panel example, we not only have a ramped thickness region, but are also able to omit material in the lower circle area to best match the final part geometry. Next slide, please. So some of the previous examples already showed a bit of this capability, but with TFP, we are not limited to traditional straight lines. So just like a 3D printer, we can just as easily follow curved paths, as you can see in these examples here. So from this feature, the example on the right specifically highlights how we can lay continuous fiber around fastener features to greatly increase effective hoop strength of the overall part. Next slide. So pathing aside, TFP also is indiscriminate of fiber material. So we have worked with not only typical fiberglass and carbon, but also thermoplastic commingled Synergex, Topreg, and even wiring. The example on the left shows a preform made of both carbon and glass, where carbon is used in the final part areas, and glass, at about 1/10 of the price, is used in the resin dam trimmed areas. In the middle example, we use TFP to accurately place 12 gauge bare copper wire within a fiberglass panel. So as you can imagine, this opens all sorts of new doors with regards to embedding wiring and circuitry within composite structures themselves. And finally, I think the example on the right is pretty interesting in that with our ability to change fiber materials on the fly, we can create structures of hybrid materials within the same laminate layer. So as we lay down the glass fibers, we intentionally leave gaps for carbon to backfill. This example to me helps highlight the versatility TFP offers, and again, the ability to optimize design and further reduce material consumption and waste. And with that, I thank you for your time, and John will take over with some industry examples.
Thanks, George. Now let's review several case studies for both lattice and lattice conductive technology. Next slide. Excuse me. This slide shows the various automotive applications we're developing with the lattice technology, including roof panels, lift gate reinforcement, door intrusion beams, floor panels, hoods, and wheelhouse inners. Next. I apologize up front, but I'm an automotive guy and live in Detroit, so my examples are mostly automotive. This example shows a hybrid carbon fiberglass fiber application for a side pole impact composite panel. The panel sits cross-car with one side attached to the center tunnel and the other side attached to the rocker panel. In the side impact test, the vehicle collides with a fixed pole at 90 degrees. Versus steel, this structure reduced crash infiltration into the passenger cabin by 45%. We converted the 2D preform into a 3D preform prior to loading in the HPRTM mold. To save cost, we included fiberglass in the outer edges of the part that are trimmed off. The project resulted in a 50% reduction in the 3D preform preparation steps and reduced waste from 50% to 0. Next slide. This application demonstrates the safety critical capability of the lattice technology. This is a door intrusion beam that goes into your door panel to minimize cabin intrusion during a side impact. Due to the safety critical nature and complex geometry, the part could not be fabricated in either NCF or UD thermoplastic tapes due to fiber movement during either thermoset or thermoplastic molding. Because of our stitching technology, we are able to precisely maintain fiber location and orientation. Additionally, the lattice easily allows for variable thickness sections. As in this part, the mounting locations on the ends have thicker sections. Next slide, please. Now to something very exciting, lattice conductive. One issue we face in composites is the metallic solutions are very competitive and well understood. We end up competing only on two metrics, cost and weight. While composites can compete, we need to change the competitive metrics to advantage ourselves versus metallics. Lattice conductive allows us to do this by incorporating electronics, circuitry, wire harnesses, plus other technologies into the composite structures and step just beyond the cost and weight competition. In this video on the top, we show the integration of a passive conductance circuit for sensing objects within the traveler path. For example, a liftgate closing with someone's hand or body in the travel path would be sensed and a collision avoided. From this liftgate example, we produced molded panels with embedded circuits and processed the panels through typical paint operations, exposing them to E-coat, prime, top coat, oven bakes. The results indicated no degradation in circuit performance. Now, I will turn the presentation over to Dan.
All right, thank you, John. And again, on behalf of INEOS Composites, want to thank everybody who's participating in this webinar and thank our friends at Coats for inviting us to be a part of it. Next slide, please. Jonathan and I'd like to share some information. First up, a little bit of information on who we are. Item 2 on here will give some examples, some current examples of our resin systems that are helping our customers meet their requirements for cost effectiveness, lightweighting, and sustainability. And then Jonathan's going to take us through some resin technologies that, when used with some of the Coats continuous fiber lattice reinforcements that we just discussed, can give the customers even greater performance for their composite system. Next slide, please. Next slide, please. So INEOS Composites is a part of INEOS, and INEOS is one of the largest chemical companies in the world. They're UK based with over 60 billion in sales, 168 global sites, and 21,000 associates. INEOS's focus is on safety, sustainability, innovation, and growth. And fortunately, INEOS Composites is a part of that growth. Next slide, please. So again, our group is INEOS Composites. Until 2019, we were known as Ashland Composites, part of Ashland Chemical. So INEOS Composites is about $1 billion in sales, over 20 global sites, and over 1,000 associates. Our primary products is thermoset resins, specifically unsaturated polyester resins and epoxy vinyl ester resin systems. We also sell gel coats and additives. Our products are used in a variety of industries, including marine, industrial, infrastructure, and as we're talking about today, transportation. The resin systems themselves can be used in a wide variety of composite processes, including SMC, BMC, LCM, resin transfer molding, diffusion, et cetera, et cetera. So they're versatile resin chemistries that can be used in multiple processes depending on the end requirements. Next slide, please. So specific to transportation, to what our customers, and by customers I mean we sell our resin systems to compounders, to molders, and in some cases OEMs directly. But again, we're coming to market with a lot of different resin systems. I'm not going to read the trade names. Aerotran, Aeropol, Enverez, Duracane are some of our most widely known products used, again, for a variety of composite molding processes. Next slide, please. So again, we're gonna talk about some current examples how our resin systems are used to meet goals, but thought we'd start with maybe a reminder slide for connecting the dots between lightweighting and environmental sustainability, which is the theme of our discussion today. So again, very specifically, how does lightweighting affect the environment? So there's some relationships that have been developed by lots of environmental agencies, government agencies, and OEMs regarding mass reduction. And specifically for internal combustion engine vehicles, 10% mass reduction translates to approximately a 6% fuel economy improvement. And again, for every gallon of gasoline that we can save, we're taking 19 pounds of greenhouse gases out of the environment. So a real popular example is the Ford F-150, which just happens to be one of the largest selling vehicles in the world. We can take 1 pound out of a Ford F-150. It can take almost 1 million pounds of greenhouse gas out of the environment. So relatively small movements in mass can make a big impact on improving our world. So that's a part of our focus on lightweighting and how it directly impacts the environment. Next slide, please. Again, now some examples of how our resin systems are used to help our customer objectives. Aerotrans 770 is one of our hybrid high performance resin systems right now, used specifically of reducing mass. Current applications include some of the exterior panels on the Chevrolet Corvette and multiple exterior panels on classic 7/8 commercial truck trailers. How it does it is by enabling the compounders and molders to significantly reduce the density of their SMC composite material. The Aerotrans 770 resin system allows them to reduce the density from what is typically 1.9 to almost 1.2 in grams per cc. This is greatly lower than the metallic materials, as noted, 55% lower than aluminum, 85% lower than steel. on a part-by-part basis to give them equivalent performance, equivalent stiffness, equivalent strength. This type of resin system and this kind of composite will result in 10 to 40% lighter parts than their metal counterparts. Next slide, please. So another example, and this is taking it a little bit farther. So now we're looking at certainly reducing the mass, but also having a direct impact on sustainability. A product we have called Envirez 1807. It's a bio-based polyester resin system. Current applications include exterior panels and general purpose reinforcements for a wide range of agricultural products, including John Deere tractors. Envirez 1807 supports mass reduction and sustainability through its use of soybean oil and corn-based ethanol that's used in its production. Each batch of Envirez 1807 that we make, which is about 38,000 pounds per batch, saves 10 barrels of crude petroleum and over 34,000 pounds of greenhouse gas emissions from the environment. Next slide, please. A further example, and this is again going even a little further. So now looking at mass reduction, sustainability, as well as value. As John touched on, as everybody on this call certainly knows, cost effectiveness is absolutely critical for transportation applications. So INEOS has a product called Aerotran 805, 2805. It's a UV resistant mold in color resin system for composite applications. Current applications as shown include the pickup bed and in-bed stowage trunk for the Honda Ridgeline and the tailgate work surface on the Ford F-150. So Aerotran 805 is used to meet the objectives in multiple ways. Being a mold and color system, it reduces the requirement for paint, which both reduces costs and is good for the environment. No VOCs are released as a result of the painting process. Additional cost savings are noted by lower tooling costs, the ability to consolidate multiple big stampings and functions and components into a single part. In the case of pickup truck beds, the use of this material means spray-on bed liners or drop-in bed liners are not required. And our customers are experiencing significantly reduced warranty costs when they use this type of composite system for items like dings, dents, scratches, and corrosion. Next slide, please. So again, I'll turn it over to Jonathan now to talk about resin systems for use with continuous fibers. Thank you.
Thanks, Dan. As Dan mentioned, INEOS has really developed a wide range of resins and resin formulations that have been effective in enhancing the sustainability in a variety of ways, but they've generally all been within the SMC framework. So I'll be discussing today how some of these same resins and the formulations that go with them can be combined with continuous fiber to address sustainability issues in even more powerful ways. Liquid composite molding, or alternative liquid compression molding, either way, abbreviated LCM, is related to SMC in the resin, filler, and additive formulation, but it doesn't have a requirement for B staging, and it doesn't have to use chopped reinforcement that's required to flow throughout the mold as it is in SMC. So instead, the reinforcement stays pretty much where you initially lay it, and the resin matrix is poured on top. So this process relies on the heat and the pressure of compression molding to distribute the matrix throughout the fiberglass. As you can tell, ensuring the resin matrix uniformly wets out the fiberglass, that's probably one of the biggest challenges in this application. The automotive interior application shown here doesn't really have very high requirements for mechanical strength, and a variety of technologies and processing techniques probably could be used. However, the use of a continuous fiberglass mat means that even less fiberglass will be needed to reach the required strength properties. By formulating with hollow glass microspheres as the filler and a relatively low amount of continuous fiberglass, the part was able to meet the modest strength properties at a really remarkable low specific gravity of 1.13. As discussed earlier, that lighter part can translate to sustainability gains in a variety of ways. As you can imagine, that continuous fiber mat could be easily substituted by a continuous fiber preform that would be even more effective at placing the reinforcing fiber at the precise points of stress that the part would experience. This very same approach can be used on an exterior automotive part, such as an equipment roof rack or running boards depicted below. These kinds of applications have much higher strength requirements, so continuous fiber LCM would be an excellent choice of molding technique. Outdoor exposure, of course, would typically require a coating to resist exposure to UV radiation. A coating such as paint would also make a less sustainable footprint for the manufacturer's operations. It would also add time and cost. The Aerotran 805 UV resistant mold and color resin that Dan showed earlier in an SMC application was incorporated here in this LCM application, and we were able to achieve high performance and tensile strength in the direction of the continuous fiber. Although the strength in the tensile mode comes chiefly from the large volume fraction of the knit fiberglass that was used, the appearance and probably also the mechanical integrity of the part after exposure to 3,000 hours of accelerated weathering here by xenon arc technique were preserved by the use of this UV resistant resin formula, where the part that we tested showed a minimal change in appearance with a DE well below 2. Parts with the highest mechanical property demands sometimes also need to be relatively lightweight, and that's why many aerospace applications opt to use continuous fiber prepreg. Continuous fiber prepreg achieves those high mechanical properties through a combination of the high volume fraction of reinforcement, uniform fiber wet out, and elimination of voids in the finished part. All of these are achievable through the unique processing and molding parameters commonly used in the prepreg industry. We show here prepreg made with the directionally balanced continuous fiberglass knit, as well as balanced carbon fiber twill. The resin does not contain reactive diluents such as styrene, which improves the sustainability of the manufacturer's operations by limiting worker exposure to hazardous materials. Also, the nature of this unique resin means that the shelf life of the prepreg extends well beyond a year, which eliminates the need for the physical and carbon footprint of a refrigeration system, while simultaneously reducing scrap from throwing out unused prepreg at the end of its shelf life, or perhaps after too much time and ambient temperatures. I will note here that we recently molded some prepreg that we've stored in our lab at ambient conditions for more than 5 years and noted virtually no difference in the tack and flexibility of the prepreg prior to molding, nor any significant difference in the molded part. The typical prepreg manufacturing techniques, like vacuum consolidation, were utilized, followed by a short cure cycle in the compression mold. In the case of the prepreg with fiberglass reinforcement, we made panels directionally balanced in the XY direction that showed very high performance in tensile strength, despite our really pretty typical specific gravity of around 1.8. You can see that tensile strength of 455 megapascals and a modulus of 21.2 gigapascals. As expected, the tensile elongation at break was relatively high when compared to the carbon fiber panels. Speaking of those carbon fiber panels, the carbon fiber panels exhibited high tensile and flexural modulus performance at a very attractive specific gravity. That's typical for continuous carbon fiber applications, of course. The carbon fiber also gave the expected enhancement to tensile and flexural strength versus the fiberglass panels. So it's easy to see how a near net shape preform with continuous fiber impregnated with the styrene-free resin could be used to create a lean and efficient manufacturing operation. So we would also be able to deliver really high performance parts and eliminate a lot of the waste, scrap, or offal, as George mentioned, that is commonly found in a prepreg process. These thinner, stronger, stiffer, high performance parts likewise could be used in myriad ways by the vehicle manufacturer to maximize efficiency and sustainability. The long shelf life of the prepreg also creates the possibility of use in a co-molding application, which I will discuss now. This final application might be the clearest depiction of the power of continuous fiber. As shown before, Airtrans 770 resin, when used in SMC, can give a lightweight, Class A cosmetic finish when formulated with glass microspheres. These left-hand columns show how, on its own, the Airtrans 770 based SMC delivers modest mechanical properties when tested in a variety of failure modes, including tensile, flexural, interlaminar shear or short beam shear, and impact. In making the panels whose properties are shown in the right-hand columns, however, we laid a small amount of continuous fiber unidirectional tape left over from the prepreg work that I just discussed underneath the SMC, orienting it in just one direction. So when the co-molded SMC and the prepreg tape were evaluated in the direction of the continuous carbon fiber, we observed really remarkable enhancements to strength and modulus, roughly doubling or tripling those values, as you can see, even though the continuous fiber prepreg amounted to really only a very small volume fraction of the finished part. The impact performance also approximately doubled, as you can see. The resin found in the unidirectional tape and the SMC are actually chemically compatible and chemically bond to one another during compression molding. And because the continuous fiber fraction added was really quite small, it didn't impact the cosmetic performance of or the specific gravity of the finished part. The placement of the unidirectional tape could mimic the potential use of a preform made with prepreg resin. The combination of these two technologies shows how simply to obtain a Class A SMC with mechanical properties of a structural SMC, or, if you will, how to obtain a high-performance structural part with Class A cosmetic properties. So these data dramatically demonstrate that even a small amount of continuous fiber, when judiciously placed, can enhance the mechanical performance of an SMC application to a really surprising degree, making a lightweight, high-performance part. In the case that the continuous fiber is prepreg scrap, the carbon footprint of the manufacturing operations is also made just that much small amount lighter. So taken together, these applications demonstrate how production-proven resins, formulated and then engineered to meet varied uses such as unpainted exterior applications, high-finish cosmetic applications, or very high mechanical performance, can be enhanced or maybe even transformed when used in conjunction with continuous fiber properly situated. This powerful combination allows the part manufacturer to deliver parts that add value to an industry, driving for ever greater efficiency, while also driving operations that are both more cost-effective and sustainable. INEOS Composites and Coats, both independently and now collaboratively, are focused on advancing new technologies with improved material properties, increased ease of processing, and reduced cost. Most significantly, though, the combination of INEOS resins on one hand and Coats preform technology on the other opens the possibility of making parts that neither the resins nor the preforms could create independently, giving customers their own greater creative freedom to drive the transportation industry forward in sustainable directions with higher performance composite materials. So on behalf of INEOS and all of us, I'd like to thank you for your time and attention. I'll now give the balance of the time back to Sarah, and she will moderate the questions from the audience regarding our presentation.
Thank you, Jonathan, and thank you, John, George, and Dan as well for what was a really insightful and great presentation. So I do have a few questions from our audience today. I hope you're all sitting comfortably, so that I'm going to just fire some, and I'll try and direct them to, if any of the others, feel free. Dan, I'm going to guess that this first one is for you, but like I said, if anyone else wants to jump in, please do. So are CAE tools and material cards available for designing, analysing products with continuous fibre reinforcements?
Yeah, thanks, Sarah. The short answer
is that one. Is that?
I'll start it. I think George might be maybe better qualified to answer from the design side. I think the short answer is yes. There's some really good tools right now for both modeling and simulating the fabrication process and how it affects the material properties that need to be used for the design itself and the design analysis. George, you can probably expand on that, on some of the tools that you're using.
Yeah, we've seen some good correlation with simulation results, but you know, as TFP kind of expands to meet different customer projects and their requirements, right? So it's an ongoing evolution into you know, understanding what our technology with different materials can do and what it can bring to the final part.
Thanks, guys. So I'm going to take this one, and I'm going to fire it at you, John Ilka. Has the concept of lattice conductive been tested through typical automotive manufacturing process simulations?
Yes, Sarah, it has. We had developed multiple different layouts and designs, and those were actually run through a automotive OEM paint process, high temperature, bake, and also the electrocoat processes to understand the effect on our, performance of the circuit process. And when we tested it, we saw we measured the resistivity of the different circuits we placed in it, and we saw no degradation in the property. So it actually performed extremely well.
Thank you, John. So I think this one is probably for both parties. So someone can start and someone else can jump in. So what are the typical cycle times for producing lattice or LCM parts?
Yes, so I will handle that. Because we're using multi-head machines, we're able to manage it on a per part basis in the 2 to 5 minute range to produce a part, depending on the complexity of the part and the size of the part. But the individual parts are longer cycle time, but because we're making 8 or 10 or 12 simultaneously, we're able to manage it down to normal automotive cycle times.
Cool. And there's another one that's kind of a little bit closely related to that one. Someone wants to know what type of tooling is required for producing lattice LCM parts. Who wants to take that one?
Jonathan, or do you want me to handle it?
So I will speak referring to the resin technology and assuming that the Coats Lattice technology is going to remain the same. So it's going to depend a lot on what kind of cosmetic finish that you want. So if you're looking for that Class A cosmetic finish that might come from the Airtrans 770 resin, your best case really is going to be chrome-plated steel tooling. But as far as what tooling will get resin cure, I think it would be safe to say that you can probably work with an aluminum tooling as well as any kind of steel. Obviously the chrome-plated finish is going to get you the best cosmetic properties that you could hope for. But we've worked with our resin with a variety of tooling. Sometimes when I mentioned the non-styrinated resin, those actually were cured just out of autoclave in the bag, so no tooling was actually required on those. So really a variety of resins can be provided given your tooling needs, and also the applications needs in the end. So
yeah, I think from a lattice perspective, Jonathan, you know, hit it. I mean, the truth is, whatever you're using to use for an NCF or a woven fabric or anything they're using today, it's the exact same tooling. Okay, you know, from composite tooling to aluminum tooling to Kirksite to steel to P20, it's all usable with the lattice. So whatever's being used today with current, you know, technologies can also be used with the lattice.
Thank you, guys. We're quickly running out of time, but I think we've got time for just a couple more final questions. So are both Coats and INEOS products that you guys have taken us through today, are they available globally?
Yes, from the INEOS side, the short answer is yes. I mean, we produce resins globally right now. Every continent has our resin plants. So the short answer from our side is yes.
From the Coats side, today we can supply them both in North America, in Europe, and we're moving towards a supply situation in Asia as we speak. So today in two areas, yes, and the third one ongoing.
Thank you. And I think that is pretty much all we have time for today, as we're coming up to our 45-minute mark. So once again, on behalf of everybody here, thank you for tuning in to today's Coatscast. As we said, we have recorded this session, so we will be sending it to you again. If any of your colleagues missed out on today, don't worry, we'll also be sending them the recording as well, and it will be available on both the INEOS and the Coats websites for you to watch in your own time. If you are interested in anything that the guys have gone through today, and we really hope that you are, make sure you're taking a screenshot of this screen now. This is how you can get in touch with John, Dan, and Jonathan on their email addresses. The other thing to point out is that both Coats and INEOS are on social media. Coats are on Instagram as well. So please do give us a follow and find out more information about all the products and services that both Coats and INEOS Composites can offer you on those social channels. So thank you very much, everyone, for watching and listening, and we'll be back with more Coatscasts soon. Bye.
Thanks all.
Bye-bye.